Thank you for joining this presentation. My name is Daneshzand and I'm a PhD student at Simon Fraser University. Today, I'll be discussing our paper called Kirfiz Exploring New Data Physicalization Opportunities from the collaboration with Charles Perrin and Sheila Carpendale. What is data physicalization and what is Kirfiz? Data physicalization, as Jason et al. Define, is a physical artifact whose geometry or material properties encode data. And Kirfiz is a new type of data physicalization that we developed based on the traditional Japanese art of kirigami. Let's now take a closer look at this type of physicalization. Kirigami, the art of paper cutting, transforms sheets of paper into beautiful and complex three-dimensional structures. The accessibility of the material, the intrinsic interactivity, the inherent static, and the possible physical variables make kirigami well suited to information visualization. We name this type of data representation that emerges at the intersection of kirigami and data physicalization, Kirfiz. Kirfiz cut pattern is formed of alternating cuts arranged in a concentric or parallel manner. Joints refer to the locations where two cuts are connected to each other, and the solid material between two cut lines is called a loop. Working with these basic elements, we can represent data with both independent and dependent variables. We can change the width and number of the joints, and similarly, width and number of loops can vary. These independent variables then affect the cut pattern's expansion amount, direction, and texture that are revealed upon interactively pushing or pulling the cut pattern. Having independent and dependent variable in Kirfiz enables physicalizing datasets with relationship in values. To illuminate this quality and some interaction possibilities of Kirfiz, we discuss one Kirfiz example, CO2 emission installation, which physicalizes CO2 emission data for the largest CO2 producers in the world. To make a fair comparisons of countries' contribution, we aim to bring both total and per capita CO2 emission to the viewer's attention. To this end, we decided to illustrate the actual relationship between these two data aspects by mapping absolute CO2 emission and population to two independent variables, the number of loops and the number of joints. Therefore, the resulting dependent variable, expansion amount, corresponds to CO2 emission per capita. We started creating the cut pattern by making an identical inner loop for all these countries. Then, in each country, for every 200 million tons of CO2 emission, we added one loop to the inner loop, which, for instance, make 4 loops in South Korea, which has 800 million tons of CO2 emission. After drawing the loops, for every 10 million of population, we make one joint in the loops, which counts as 4 in South Korea with approximately 40 million population. We do the same data mapping practice for all the countries, and this is the resulting cut pattern. The overall size of each cut pattern shows the overall CO2 emission in that country. Therefore, one can quickly observe and make cross-country comparisons to make a ballpark estimation of the differences. Upon closer examination, the viewer can also retrieve precise values by counting the number of loops and multiplying that by 200. The per capita emission of countries is revealed by interacting with Kirfiz. Number of joints in a cut pattern is proportional to the population. Therefore, the larger the population, the denser the texture of the expansion. With total emission represented through cut pattern size and population through texture density, the amount to which each country expands represents emission per capita. The viewer can expand several cut patterns to compare different countries based on their overall emission amount, population, and per capita emission. To understand how people interact with Kirfiz, we conducted an exploratory qualitative study and studied the participants' behavior while they were exploring data through 4 Kirfiz examples: the CO2 emission installation, a Kirfiz family calendar, activity jewelry, and productivity coaster. Our 12 participants range from 19 and 64 years old, and 5 were female. For each Kirfiz, we prompt their exploration of the dataset through a mix of scenarios and also by asking some simple questions, for example, to retrieve a value, find extremum, and sort values. Participants were encouraged to speak their thoughts aloud while manipulating the curves. After their exploration, they took part in a semi-structured interview in which they were asked about their overall experience interacting with curves. We analyzed the transcripts through iterations of open coding and meetings with the research team. As a group, we iteratively constructed the emerging teams to capture the perceptions and impressions of the participants. The study results are grouped under three overarching themes: comprehension, interaction, and curves in context. I will present a few highlights from comprehension and interaction. Please refer to the paper for full findings. On engaging their first curves, all participants spontaneously expressed positive reactions, such as "very cool expansion texture," "it feels satisfying to hold and expand." They also expressed joy by saying, "Oh, this is really beautiful." Also, while 5 participants started immediately touching and stretching the curves, 7 participants hesitated to interact because of the curves' delicacy. Wow, what if I tear? This study also allowed us to observe how people read curves variables throughout the examples. We learned that understanding curves variables required initial explanation, but once learned, the variables were readily understandable. For example, P1 said, "They're kinda easy to understand once you get the mapping right." About interactions, all participants liked curves interaction possibilities and indicated it encouraged them to discover meaning and kept them engaged. They used expressions like "triggers my curiosity," "intriguing data representation," "playful and enjoyable process." This experience is well described by P9, who said, "I think it's kind of like a puzzle. I like doing puzzles and trying to figure things out. I feel curious and then I can focus on it maybe more easily because I'm trying to figure things out step by step. It feels stimulating." 10 participants perceived the elasticity of expansion as the most distinguished variable and utilized it to analyze the data and compare different cut patterns. For instance, while manipulating the weekly curves coasters, P10 explained, "Through the interaction, I had a sense of the weeks based on the expansion density and resistance. Counting helped me to verify my feeling or intuitions." To describe this sensation, they actively use expressions like resistant to expansion, springiness, toughness. They especially use the expansion elasticity to make comparisons and explain their feelings with terms such as easier to pull or harder to pull or denser. Curves opens up a broad range of design possibilities. Depending on purpose and context, curves with different shapes, patterns, configurations, and reconfiguration can be created. Curves is potentially inexpensive and often portable through the use of 2D material and common cutting tools. Curves has representational functionality on a wide range of scales, from very small, like jewelry pieces, to architectural scale. Also, many choices of material, as inexpensive as paper to fabric and thin metal sheet, are open to physicalization designer. Regarding interaction, curves support non-technical tangible interactions as well as the creation of technology-based dynamic physicalization. We hope that this work will inspire future tangible data representation and the design of more delightful and intriguing interactive data physicalizations for engaging people with data. Thank you for watching this presentation.